cosine, right? Cosine of omega t was s over s2 plus omega 2. Whenever you multiply an exponential by something, it means that you're gonna have a shift in your s. So this is now gonna become s plus alpha and s plus alpha squared instead of just s, right? So this is what we have. And again, if you take inverse Laplace transform, it would give us the time domain. Okay, so this is very similar to what we have here. Okay, so if I look at s plus 1 divided by s2 plus 2s plus 2, I can write this as s plus alpha. I want to write it in this term, similar to this format. So this is going to be s2 plus 2 alpha s plus alpha squared plus omega 2. And I want to know what's alpha and what's omega. Okay, so if you look at these two, you see that alpha is equal to 1, and if you just like simplify this, you would find that omega is going to be equal to 1. So if I actually take the oh, I shouldn't erase this one. So if I take inverse Laplace transform of this, it's gonna be e to power negative t times cosine of t. Okay, as t goes to infinity, this is bounded, this is like between plus minus 1. As t goes to infinity, this goes to 0. So the whole thing is going to go to 0. So this shows that this is stable. But how does it look like? It's actually going to look like something like this. If this is e to power negative t, this is e to power negative t, and this is going to be its mirror with respect to the t-axis. So this is, let's call it f of t, g of t. So our waveform is actually going to look like this. It's oscillatory, but eventually becomes 0. So it is stable, but it has a different waveform than the waveforms that we saw before. So this is the impact of having an imaginary, a complex root. When you have imaginary component in your root, you would have some oscillation. You remember, like we mentioned, that anything on the imaginary axis correspond to a frequency. So this is basically what's happening here, and the frequency here is if you look at this, this is 2 pi f times t, right? So the frequency here is actually 1 over 2 pi. Okay, so this is the frequency of the oscillation that you see here. So that's the impact of having complex roots. Okay, so just to summarize, if all your poles are in the left plane, your system, it's going to be asymptotically stable, or stable in short. If you have at least one pole on the right side, the system, it's going to be unstable. Okay, and if you have like a root on the imaginary axis, that means that you're gonna have marginally stable response. How about zeros? So we talked about the poles of the transfer function, but I didn't mention anything about the zeros. So first of all, when you have a transfer function, if it's the general term like alpha s to power n plus beta s to power n minus 1 plus kn, and a s to power m plus b s to power m minus 1 plus km. Zeros are the s values that makes the numerator equal to 0. Numerator equal to 0. Poles are the s values that makes the denominator equal to 0. Okay, so let's just, like, using an example, see what happens if our system has some poles, and see what the impact of having poles are on response are. So let's say that we have just like signal that would give us this kind of performance. Okay, so this is actually a marginally stable thing, like a marginally stable response. So C of t is gonna look like this, right? So let's assume that this is a signal we have. It just like has one pole, and it has this marginally stable response. Why is it marginally stable? Because it doesn't go to 0, it doesn't go to infinity, it just gets stabilized at a certain point. Now I want to add a 0 to this transfer function, or to this signal. So it means that I want to see what happens if we have a 0 to this, if we add a 0 to this transfer function. So like this could have been something like 1 to power s plus something, like s plus alpha or something like that. But like 1 over s plus something else, like let's call it m or something. But now we want to add a 0 to the transfer function. So this basically means that our system is now going to be s times c of s plus alpha times c of s. Now, what happens if I take inverse Laplace transform of this one? S c of s, if I take inverse Laplace transform of this one, it's the same as dc of t dt, right? We did the opposite thing, like when we have like a derivative, if you take Laplace transform, becomes s cs. Now I'm just doing the inverse Laplace transform, and this one is just going to be alpha c of t. Okay, so this is now, so like if we have a pole, if you have a 0, now